Hi, in this week, we will talk about boundaries and how to find specific shapes on images. When we calculate the edges of a given image, we might end up with many lines. But what if we only want to find the contour of the object to apply certain procedure to that specific region? Here is where active contours can be helpful. This algorithm is also known as snakes, and it works kind of like an elastic band. The idea is to create a shape that will move into the object until it reaches the edge, covering it from different directions and stopping when it touches it. Just like when you use an elastic band to hold things. So let's see how it works. We need to start by defining a group of points that are separate by the same distance, and this will act as our contour. This can be a vector v where each point has coordinates x and y. The contour should be large enough to cover all the area of the desired object. Remember that it works as an elastic band, so once that we start the algorithm, it will shrink. Then we need something to attract the band to stop it. And because we are interested in finding the outer edge, we can use the gradient magnitude of the image. One way to increment the effects of the gradient magnitude is to square the gradient and then apply smoothing to extend the area of the magnitude. Then the goal is to maximize the sum of the gradient magnitude square in all the points of the contour. Then the algorithm has two main steps. For each point in the contour, we will move the point to the location with the higher gradient magnitude value within a window. Then we compare the new location of each point with its previous one. And if the location changed, you go back to one and repeat. But if the location didn't change, then you are done. This can be easily modified to show the opposite behavior. So instead of shrinking, we can expand our contour in a similar way as if we inflate a balloon. The only difference is that when we shrink, we don't need to worry about the number of points, because most of the time, the points will get closer to each other on every iteration. However, if we expanding the balloon, the points of the contour are moving away from each other. Then we will need to create new points to avoid large space between points. In this simple version, each point is moving independently, making the algorithm susceptible to noise, possibly resulting in deformed contours. So we can apply two constraints to help our algorithm to behave more like an elastic band. The first will take care of the rapid changes because we want that all the points move at the same pace. And with the second, we will take care of the shape because we want a smooth curve without the spikes. Of course, if your application requires more or less of these characteristics, you can weight each of the constraints according to your needs. So now we have the energy of the contour that is given by the elastic component plus the smooth component. And because those are the first and the second derivative of the contour, we can estimate them using the finite difference. So we define this as the internal bending energy of the contour that is given by the sum of energy of all the points that forms the contour. Now the algorithm will combine the bending energy of the whole contour as well as the attracting energy of the magnitude of the object, of the edge that we are looking for. One detail here is that in our first example, we wanted to maximize the sum of squares of the attracting energy. But now that we have other components, it's more convenient to use the inverse of the attracting energy and the algorithm will try to minimize the total energy of the system. We should notice that this algorithm can work really well, but it needs to be initialized in the right place. And as you saw in the example, some kind of processing needs to be applied before to clean the area. Okay, in this video, we talk about boundaries, and we review the active contour algorithm. See you in the next video.